Welcome to part two of the lecture of volcanoes and igneous processes. In part one, we talked about the concept of viscosity and lava composition and how viscosity and composition can influence different types of volcanic lava flows. For example, we looked at mafic type lava flows, which incorporated the Pahoehoe and Aa type lava flows. We looked at the felsic type lava flows, in which we looked at various types of ejecta material that exits a volcano. In this case, most of them are very explosive type eruptions in the felsic type. So in part two, in this lecture, we're going to take concepts from part one in terms of viscosity and composition and the types of flows, and we're going to look at three types or three dominant main types of volcanoes. Then we'll look at some volcanic features associated with these volcanoes. And then towards the end of this lecture, we'll look at plate tectonic processes and how some of these plate tectonic processes produce these three types of volcanoes. So our first type of volcano we're going to look at will be known as the shield volcano. And then we'll move to the composite volcano, sometimes known as the stratocomposite or stratovolcano. And then we'll look at the cinder cone. And really, when you explain the differences with respect to each one of these volcanoes, you can just really look at the pictures. And the pictures kind of give rise to different types of lava flows, which is really dependent on silica content, which we learned from the first part of the lecture, that silica content can certainly influence viscosity. So each one of these types of volcanoes, again, are very dependent on how much silica is in the volcano itself. So our first volcano we're going to look at is known as the shield volcano, and probably one of the best examples to show a shield type volcano is in the Hawaiian Islands. And these particular volcanoes, the shield volcanoes, really is just formed by the accumulation or stacking of fluid basalt flows. And notice we say fluid basalt flows. These fluid basalt flows are low silica content. They're basaltic composition, meaning that they're very high in iron and magnesium, again, low silica. And because of the low silica content, again, we learned from part one of the volcano lecture that the low silica shows a low viscosity, which basically represents less than 1% pyroclastic debris. So this would tell you then that because the pyroclastic debris is less than 1%, these particular types of volcanoes, these shield volcanoes, are very non-explosive eruptions. And they're very common with Pahoehoe and type flows. And non-explosive eruptions mean you really, in some cases, if you can take the heat, can get right next to the flow itself because it's so fluid that the flow will basically just run along pre-existing valleys and so forth. And typically a shield volcano is described as or known as a type of volcano in which the flanks, the sides of the volcano are very broad and very low angled type flanks, which lends itself to the term shield. Because if you look at a cross-sectional view of a typical shield volcano, it would resemble a shield. And this white line here kind of shows you that broad, low angle flank. So common shield volcanoes found on Earth certainly would be the Hawaiian Islands, Iceland, the Galapagos Islands, and commonly shield volcanoes will rise along the ocean floor, the deep ocean floor. And again, it's where the chemistry lends itself to basaltic type flows, rich in iron and magnesium and very low in silica. The next volcano would be the stratocomposite volcano, again, sometimes known as the stratovolcano, sometimes known as the composite volcano. And The strata composite volcanoes typically form from layering deposits of ash, lava, and pyroclastic flows. So typically, if you were to cut open a composite volcano and look at the cross-sectional view, you would observe these layering effects of ash, lava, and pyroclastic flows. These volcanoes, the composite volcanoes, are very high in silica, in this case up to 70%, rhyolitic composition, which now gives rise to very high pasty viscosity type flows. And with this high pasty type um, nature of the flow, material can't move very fast, and so you get abundant pyroclastic activity, which really translates into deadly airborne types of debris and very explosive type eruptions. And so these composite volcanoes then are very hazardous. And certainly when a composite volcano erupts and we get the types of pyroclastic material exiting the volcano, it certainly makes the news. So these high silica rhyolitic composition composite volcanoes, again, are very deadly. And then, of course, if you look at the picture here, you can see that we got pyroclastic material. This is an example of a neurodont gas cloud that's exiting the volcano. And again, as we described in part one of the lecture, neurodont clouds are very dense, laden, high heat uh, um, clouds that roll down the sides of the flanks of the volcano at really high rates of speed, somewhere in excess of sometimes 200 miles per hour. And one of the features that outlines a composite volcano is the fact that it contains steep, high angle flanks. And if you think about that, that's a lot different than the shield volcano, because remember, the shield volcano is basically a very fluid type volcano. So geomorphically, when it forms its characteristics or flanks, again, they're broad sheets. But being a composite volcano with a very high viscosity, pasty type flow, it has a tendency to build up the volcano into these high angle, steep flanks. Composite cones, again, composite cones are very common along the western U.S. coast. This would be the Cascade Mountain Range, in which there are at least 10 or more stratocomposite volcanoes comprising the Cascade Mountains, in which one of them was Mount St. Helens in the southwestern part of Washington State, and then western South America coast, and of course Japan. The island of Japan houses a few of these big composite cones. Again, plate tectonic wise, which we'll discuss a little bit more in detail, but the composite volcano typically will form in the ocean along these convergent boundaries. And later on, we'll show in which plate tectonics can describe the plate setting to allow these big composite volcanoes to form. And found along the Ring of Fire. So if you recall, the discussion in plate tectonics, the Ring of Fire basically is a set of volcanoes and earthquake activities that circumvent around the entire Pacific Ocean rim. Cinder cones, sometimes known as scoria cones, exist all over the Earth's surface, typically by the thousands. In fact, characteristically, you can find what we call volcanic fields or cinder cone fields. One in particular, located in Flagstaff, Arizona. There's actually approximately 600 of these different types of volcanoes. And typically, a cinder cone is a small type of volcano, much smaller than a composite cone, much smaller than a shield volcano. They're characterized by very high, steep, angled flanks, 30 to 40 degrees in angle. These cinder cones average about 1,000 or 100 feet to 1,000 feet high. So relatively speaking, they're a lot smaller than a composite cone. But again, there are many of them. And again, we can find them in volcanic fields. They're known for a pyroclastic material that's erupting They're known for basaltic type flows and so forth. And so here in this particular slide is a picture of a typical cinder cone. And I believe this one is actually from the Arizona area. And again, cinder cones are formed by basaltic flows, can be basaltic flows, gas-rich basaltic flows, low silica, typically producing smaller sized material. The common rock associated with cinder cones are the rock scoria, which actually is a very porous type vesicular extrusive igneous rock that's typically dark in color, could be light in color, which would be called a pumice at that time. A lot of these rocks are used for landscaping, but we can find, again, vesicular textures with glass. Single eruptive episodes, sometimes they last for a very short time. 95% of these volcanoes just pop up and form less than 1 year. Again, composed of scoria loose pyroclastic material. Cinder cones can also form as a parasitic type cone. And if we learn from the first discussion in part 1, we know that parasitic type cones can be smaller cones that rest along the flanks of the larger volcanoes. So you can really have cinder cones along flanks of a composite cone. One of the most famous cinder cones that recorded in history, since geologists have been watching volcanoes form, is the Paricutin Cinder Cone. And this is a cone that formed 200 miles west of the Mexico City. This particular cone actually erupted in a cornfield in 1943. And the story goes in which the farmer was hoeing and tending to his field, and the eruption began in his cornfield. And in one day, the particular cinder cone in Paricutin grew 130 feet in one day. And this took place in June 1944. Because of the lower volatile gas content, it really formed a lot of 30-foot thick flows, which emanated from the volcano, which you can see in the background, and buried this particular village. So you can kind of look at the picture here. And in one day, again, 130 feet and extensive type flows. And then by 1952, the volcano just ceased. And it completely, changed the landscape, changed the living accommodations of the village, and so forth. Basically, in one day and during that 44 to 52 time duration. And so again, if you look at the slide, you can see the cinder cone in the background right here. Cinder cone, and of course, I believe this is a steeple of a church within the village. And there it is, the Paricutin Cinder Cone, if I'm pronouncing it correctly. Here are some views of particular types of cinder cones. And again, they all take on the characteristics of very steep type flanks, very small in size, relatively speaking, when you compare it to composite cones. And again, they're, again, 600 to 1,000 feet high. Okay, other volcanic landforms. We're going to take a look at calderas, volcanic fissures, and we're going to look at various exposed internal parts of volcanoes, known as volcanic pipes and necks. So in the first view here, we have what we call a caldera. And a caldera represents large depressions, basically located at the top of the volcano. And in most cases, the caldera is in excess of a mile in diameter. And calderas form in various ways. And I have listed here in the following ways. Really, a caldera represents a collapsed summit, top of the volcano, following typically of an explosive rich type of eruption. And this example I'm showing you here is Crater Lake, for example. And you can see that this makes the composite cone right here. And then the composite cone explodes, and then it collapses. And as it collapses, it makes a depression. And typically that depression will fill with water. and then basically forms a lake in the top of the crater. And so this would be known as a caldera. And you can see down here in the picture, this is a collapsed caldera that's been filled with lake water. Collapse of a shield volcano, again, similar, where the top of the volcano collapses and collapses from the drainage of the central magma chamber. And this would be typical of the Hawaiian Islands, which I think I have a picture coming up after this one. Collapse of a large area from a discharge of volumes of high silica, rich in pyroclastic materials. So these are some ways in which a caldera can form within a volcano. The bottom line here is that really the caldera represents just a large depression in the top of the volcano. And by definition, a caldera is about a mile in diameter. Here is a collapsed volcano from the drainage of a magma chamber in the Hawaiian Islands. And so here you can see in the map view, you have various calderas that are formed from that collapse of the magma chamber draining, and then been actually marked 1974, here's one, 74, and so forth. So you can kind of see where the caldera kind of moves around. Another very known type of caldera is known as the Long Valley caldera. And the Long Valley caldera is located, I believe, on the eastern side of the Sierra Nevadas. It's a very large caldera. It's at least 20 miles in diameter. And this is a result of a collapse of volumes of high rich silica pyroclastic materials. And so again, you can see where the silica-rich magma collects at the top, and then the roof of the magma chamber collapses right here. And upon collapsing, a depression is formed, and it produces a large depression or caldera here. And in this photograph down here, you can actually see the length of the caldera. It stretches about 20 miles. And again, this is located on the eastern part of the Sierra Nevadas, and it's known as the Long Valley caldera. And sometimes when you're driving on the eastern part of the Sierra Nevadas, you drive up a really steep flank, and you don't even really know it. The altitude of the highway just gets higher and higher until you reach the summit or the top of the caldera. Another type of igneous feature is, I have listed up here, you see extensive lava flows, but where is the volcano? In other words, you see thick sequences or thick deposits of volcanoes or of lava. But again, the question is, where is the volcano? Well, in this case, the volcano really doesn't exist because these are known as fissure type eruptions or lava plateaus. And these represent very fluid, mafic basalted lava that really emanate and erupt from fractures in the Earth's crust. And what it really produces, if you can envision a series of cracks along the Earth's crust, and producing a series of what we call lava fountains. And these would be linear fractures that spread out over wide areas. And up from these linear fractures, then erupts a lot of these fissures. And typically in a fissure type eruption, voluminous or large amounts of basaltic flows are extruded, and these are low silica basaltic type flows, which means that the viscosity is going to be low, which means that these particular lava flows can extend over large geographical areas, because basically they're just running type basalts. And so in some cases, a single flow can travel hundreds and hundreds of kilometers with these fissure type eruptions. And one of the best known types of fissure eruptions is known as the Columbia River basalts. And if you look at the map in the lower left-hand corner, this is a map showing Washington State, Oregon, a little bit of Northern California, and the southern part of Idaho, along with the little northern part of Idaho here. And these are all an accumulation of basalts that have happened over a 17 million year fissure eruption. And these are very extensive. It's been known that one single flow can emanate from this part of Idaho and make one single flow all the way to the Portland, Oregon area. And in some cases, in the southwestern part of the state of Washington, some of these Columbia River basalts can be a mile thick. And so, can you imagine standing up in the high mountains here in Idaho 17 million years ago and watching all the tectonic activity um, splitting fractures in the crust and watching these fissure type flows, these huge lava fountains just flood the area with basalts. I put here when I was working on my graduate degree, my master's degree in geology, my study area included a portion of the Columbia River basalts, and my study area was up in the northern part of Idaho, where I have it circled right here. So I did a lot of extensive studies of the Columbia River basalts. This is a picture of the Columbia River basalts. This is in the southeastern part of Washington State. And certainly you can see the extensive amount of flows that had taken place over that 17 million year time period. And this represents a mile thick of basalt flows. So starting at the bottom and working your way all the way up to the very top here. And so you can imagine layer upon layer upon layer of basalt basically being flooded throughout that region of Oregon, Washington, and part of Northern California. And if you ever get a chance to take a drive to the Washington State, Oregon border area, you'll drive right through the most thickest part of the Columbia River basalts. And on both sides of the highway, the stack or the layering of basalt is tremendous. It's a half a mile to a mile high. Lava domes basically represent what I like to call a plug that's found in the crater of the volcano. And basically, these are lava domes are very characteristic of a composite volcano. And these represent very thick, rich silica lavas. When we say very rhyolitic in composition, we're saying very felsic. And these typical plugs are squeezed out of the volcanic vent. They form slowly over time, and basically they can form along volcanic flames as well. This particular lava dome you can see is right in the middle of the crater of the volcano, and it's basically solidifying and plugging up the neck. I believe that this particular picture we're looking at is actually Mount St. Helens, and so Mount St. Helens now has morphed from a actual composite volcano into more of a plugged dome volcano. And really it just kind of indicates that the volcano is still active. And it's just forming these little rhyolitic plugs along the crater area. Volcanic pipes and necks. These are known as what we call diatremes. And a diatreme basically is a type of volcanic deposit that originates about 200 kilometers or 125 kilometers or 125 miles below the Earth's surface. And this is where magma rapidly ascends from that depth up to the surface of the Earth. And in this case, there's really little alteration to the magma. And it's characteristic of a very high pressure temperature minerals. This is where you are going to find your diamonds. Diamonds are very common in these types of deposits. And really, these diatremes, these volcanic pipes, are considered windows to the Earth's interior because of the rapid ascending of the magma that makes its way to the surface. And the best known diatremes are what we call the kimberlite diatremes in South Africa. And this is where material is being brought up to the Earth's surface with respect to what we call a kimberlite. And this is where we can find raw diamonds. And if you look at the slide or the picture in the bottom of your slide, you'll notice that here are some raw diamonds. There's a diamond incorporated into this kimberlite type rock. Shiprock, New Mexico, another very famous area to show remnants of volcanic activity, and another area that shows the remnants of the internal parts of a volcano. This is known as Shiprock, New Mexico. The rock itself stands about 1,380 feet. These are rhyolitic, felsic composition type remnants of the volcanic neck and the dike that extends from the volcanic neck. And really, the reason why these exist is because these particular rocks are much more resistant to weathering processes than the surrounding rock. And so, throughout geologic time, the less resistant rock material has been eroded and moved away. Less standing is the internal parts of the volcano. And so, here again, you can see the volcanic neck right here, and then you can see the volcanic dike that extends away from the neck. And at one time, this probably was a very large composite volcano. Certainly at that time, the neck was not exposed, but here in this case, it is now exposed. Some features that are associated with volcanoes, some igneous type features. I believe we've discussed this a little bit when we looked at rocks. But here's just another picture view of some terms that are given for various volcanic features. This term here, dike, is a type of igneous feature characterized by the fact that it cuts across layers. And so here you can see where this is what we call a disconcordant type feature cutting across the volcano. Here is a sill, and a sill basically is a type of solidified igneous rock feature that's parallel to overlying rock material. And then here's another dike. Here you can see it's cutting across the strata. A laccolith basically is characterized by a mushroomed type shaped dome igneous feature. And then, of course, we talked earlier, I think, in past discussions about the batholith. And the batholith is a huge solidified granitic type rock below the Earth's surface. And by definition, a batholith has to be more than 40 square miles. Any irregular igneous body less than 40 square miles is known as a stock. So this is just a pictorial view of some of the terminology that geologists use to describe different kinds of igneous features. So let's look a little bit at igneous activity and the relationship between plate tectonics. And as you recall from the plate tectonics lecture, indicated that plate tectonics is regarded as the universal theory. And it really is true, because now with the onset of plate tectonics and how plate tectonics works, it's very easy to describe why the three types of volcanoes exist where they do on the Earth's surface. And it's really related to two things: the plate boundary, in terms of how the plates interact with one another, and from the plate boundary, it's related to the chemistry. And so really, if you haven't realized this yet, the Earth that you live on basically is one big chemistry set. So if we look at divergent plate volcanisms, here we know that the plates are being separated, they're being spread apart. And if we look at the ocean floor, we also know that the ocean floor is primarily mafic. And so from divergent plate volcanism, we have basaltic magma that's ascending into the fractures. And because it's mostly basaltic, it's mostly sea floor, compositionally and chemistry-wise, really the Earth is erupting low silica, low viscosity, and runny, non-explosive type features. And so again, as we said earlier, it's very common then on the ocean floor to find shield type volcanoes. And because the divergent boundary sets up the boundary itself and the composition. If we move to the ocean to ocean plate convergence, here we have an ocean plate now being subducted beneath an ocean plate being subducted beneath a continental plate. And so now the melting subducted plate then, as we learned in the plate tectonics lecture, the subducted oceanic plate begins to melt, and as it melts, it's now producing basaltic type magmas. So again, very mafic, low in silica, and it comes in contact with other ocean floor, which is again mafic, low silica. So in terms of chemistry, we're producing, we're allowing melted material to come in melted ocean material to come in contact with other ocean material. So we're putting basaltic with basaltic. And so what would you expect to form then in terms of an ocean to ocean plate convergence? Well, you're going to form what we call island arc systems or more shield type volcanoes, because the chemistry lends itself to basalt. So an ocean to ocean plate convergence, again, typically will form shield type basaltic volcanoes as island arc systems. And some examples there would, of course, be the Japan, the island of Japan, and the Aleutian Islands. If we move down to the next plate scenario, we have ocean to continent plate convergence. And here we have oceanic plate now is being subducted beneath the continental plate. And of course, the melting basaltic ocean plate now begins to ascend. But what happens in this case is the basaltic low silica plate then begins to mix and come in contact with continental plate. And we know that when we look at continental plate, it's very granitic / rhyolitic in composition, very felsic. So now we're mixing the ocean plate with higher felsic material. And now what's happening is along the continent, the formation of composite volcanoes take place because of the high silica, because of the introduction of silica from the continent. So now we produce high silica, high viscous, explosive chains of volcanoes. And so these are known as the composite volcanoes. And so this is a really good example of the cascade volcanoes in the western United States and along the western side of Chile as the Andes Mountains. So you can see in this picture, we have composite volcanoes forming along the coast. And this is where, again, we get Mount St. Helens and so forth. So really, most composite volcanoes then, therefore, exist along the margins and coast of continents, which would be reasonable given the plate tectonic setting. But unfortunate for us, because most societies live along the margins of continents. And so we have to contend with these big composite explosive type volcanoes. The last, if you look at the bottom of the screen, the last plate boundary is known as an intraplate hotspot boundary. And I don't believe I discussed this too much in the plate tectonic lecture, but really what we have is a hotspot in which decompression melting allows magma to form. And upon forming and being less dense, the magma ascends upward, interacting with oceanic plate. So again, here you have basaltic material being formed from decompression, and you have reacting with oceanic plate, which is also basaltic material. So you have basaltic reacting with basaltic, which is going to give you mafic type compositions, low silica, low viscosity. And then really in the intraplate hotspot, when we say hotspot, we're talking at the hotspot is very stationary. It doesn't move. However, the plate itself moves across or over the hotspot or the decompression zone. And as a result of the plate moving over the hotspot, it forms a series of shield type volcanoes. And so if you look at the bottom diagram, you see the Pacific plate, and you can see where the Pacific plate is basically, there's the arrows basically moving or sliding over the stationary hotspot. And in each situation, it creates a shield volcano that pops up. And of course, the classic example for the intraplate hotspot volcanoes, shield volcanoes, would be the Hawaiian Islands. And so this is a very important slide because it brings together igneous activity, the type of volcano, with the relationship between plate tectonics. So at this point, you should now be able to think about the plate boundaries with respect to discussions that we had earlier, lectures on plate tectonics, and bring that together to be able to describe now the different types of volcanoes that can occur on the Earth's surface. And you should be able to take the relationship of the plate tectonic boundary and relate that to the chemistry in terms of why we see composite volcanoes on the coast of continents and why we mostly see shield type volcanoes emanating from the ocean floor and as islands. It truly is that plate tectonics is a universal theory.